As we start to look at polar graphs, it's sort of like starting over. You have a really good idea of a lot of Cartesian graphs, polynomials, trig functions, whatever. And so you really don't have any intuition, given a polar curve, what it's going to look like. So we're going to stick to sort of a toolkit of several curves and use those till we get comfortable with them. So I want to start with one of those today, and that is something as simple as r equals sine theta. So there's a couple of ways of going about trying to figure out what that looks like. Would be to plot some points, but I don't want to do that because I don't know how many points are going to be enough to see the real behavior. Should I have them? How far apart should they be spaced? So I want to try an algebraic approach and an approach that uses what we know of sine already. So the algebraic approach would be to try and convert that to some Cartesian equation that we know. And the other is to graph this into a space on an r and theta axis. Actually, let me do that one first. Let's take a look. So not in xy space. So this is not the polar curve, but I just want to think of that as a Cartesian equation on a theta and r axis here. So we know what sine looks like in this space, right? R equals sine theta. Looks something like that. And we know where some key behaviors happen as far as where the peaks and valleys are, when it's going up, when it's going down. So let's think about what that tells us about the polar graph. So let's think about graphing in polar coordinates in the xy plane. So as we move along here, we are going, let's look at this graph as we move left to right. So as we move left to right, we're getting bigger and bigger theta, which in the polar plane here means rotating around counterclockwise. So we start off facing this way, a theta of 0, and at that point r is 0. So that's a key point. We're at the origin. So actually, every time this graph comes into contact with that axis represents an r of 0, which means you're back at the origin. So we can translate what we know about intercepts to what will end up being points at which the curve passes through the origin. Now, what else does this graph tell us? Well, as it's moving up here to this peak, that whole time r is increasing, right? Well, as you're rotating around, an increasing r means you're spiraling out. So that tells me that the behavior there is a spiraling out behavior. And all the way until pi over 2, I'm spiraling out, and I max out at a radius of 1. So from 0 to pi over 2, I'm going to spiral out and end up at the maximum radius there of 1. Now, here, this whole time from pi over 2 to pi, I have r decreasing, right? Well, a decreasing r means you're closer and closer to the origin or spiraling in. So that's a spiral in. And so that corresponds to something like that. When we get around to pi, which means facing that way, we're back to an r of 0. So we started out at 0, spiraled out to 1, spiraled back into 0. So really what you can do in this theta r space is just look at where are my intercepts, which hopefully we already know that about the behavior of that function. That's going to be every time you enter the origin. Every time you're moving away from this theta axis, you're spiraling out. Every time you're moving towards that theta axis, you're spiraling back in. Now, where it gets a little tricky to think about is in these regions where we're in the negative r's. So remember, a negative r in polar means plotted as a projection through the origin, or a reflection through the origin, if you will. So as we come through pi over 2 to 3 pi, or excuse me, pi to 3 pi over 2, so the third quadrant, the whole time we're in the third quadrant, so from there to there, we are spiraling out, but we're not spiraling out in this quadrant because our r's are negative. We're spiraling out in the first quadrant. So nothing is going to show up here in the third quadrant. Actually, that piece from pi to 3 pi over 2, we are drawing this again. So we get that half of the curve again until we get to here where we're at an r of -1. So when we're pointing down 3 pi over 2 and go backwards 1, we're back there at our peak. And again, from 3 pi over 2 to 2 pi, r is negative but spiraling in. So we're not going to draw anything in the fourth quadrant. It's going to be over here in the second quadrant. So as we sweep through the fourth quadrant, we draw that piece. We spiral in. So actually, we draw the same shape twice. Once for the positive. So from 0 to pi, we get that. And from pi to 2 pi, we get it again. We're just drawing it once with positive r's and once with negative r's. And because of the periodicity of sine, that process just repeats over and over and over again. So we get this shape really only looking at two things. Where is r0? So when are we at the origin? And when are we spiraling out or spiraling in? Because essentially that's all that can happen in polar, right? R is either getting bigger or smaller, or I guess possibly staying the same. So that gives us a rough, it looks like a circle. It's a rough sketch though. We're not sure if that's exactly circular. And that's where the algebra would come in. So the other approach would be to try and convert this via our conversion equation. So remember in polar, x is r cosine, y is r sine. And x squared plus y squared is r squared. And tangent of theta is y over x. So we want to try and use these to convert this to a Cartesian equation that we would recognize. So r equals sine theta. So there's no hard and fast rules about how to do this. You just use whatever's convenient up there to convert all your r's and thetas over. So sine is right here in my equations. But it'd be great if it had an r on it, because then I could, if this was r sine, I could just replace it with y. Also, this would be great if it was an r squared, because I could replace it with x squared plus y squared. So what I'm going to do is multiply by the same thing on both sides, which we know we can do there. So r squared is r sine theta. And now I can use my conversion equations. R sine is y. Now we remember from algebra that something that looks like this is a circle. It's not in standard form, but because it's got x squared, y squared, and then possibly first degree powers of x and y. So it's somewhere shifted away from the origin. So remember what we do to get it into standard form, we complete the square. So move that y over, completing the square. Remember, you take half that coefficient. That coefficient is -1. So half of that is -1/2. Square it is 1/4. So I'm going to add 1/4. Not sure why I didn't add that on to the end, but key is that's now a perfect square. That's y minus 1/2 squared. And that, we know, is a circle with a center at 0, a half, and radius a half, which is exactly what this looks like, right? A circle with center at 0, 1/2 with a radius of 1/2. So that really is a circle. It may have been a little bit elongated. It was hard to tell just by a rough sketch, but the algebra lets us know that really is a circle. So two different approaches. One is relying on what you know from Cartesian, so converting it to Cartesian to sketch the graph. This approach is nice because it can be difficult sometimes to do this conversion, but if we can just do a sketch in the theta r space, we can easily just analyze the spiraling in and the spiraling out and get a rough sketch anyways of what it looks like. Oh yeah, Desmos. So yeah, something closely related to this is r equal cosine. Let's take a look at that. So if you think about what we were just doing with that theta r space, r equal cosine would look exactly the same, but just shifted, right? Cosine and sine are just shifted in theta. Well, shifting in theta is a rotation about the origin, right? Because in polar, and let me do this. What's nice in Desmos is you can put this into a polar grid instead of Cartesian. So now what we have are lines here at the common thetas and then circles at the various r's. So we're really just moving forward in theta. And so really all that analysis we did would be similar for cosine. And we'll see this with other graphs we look at in polar, that if you can understand what it looks like with the sine function, the cosine function is just going to be a rotation about the center. Really, we could make that circle be anywhere just by taking sine and shifting it. Now, we could also play around with this a little bit. Let's turn off cosine. I've got a couple of parameters here. The first one is just a multiplier. So think about that c out front. It's going to make all the r's bigger. So it's just going to blow up that circle and make it larger or smaller depending on whether c is bigger than or less than 1. Because every r gets increased, and an increasing r means farther from the origin. So that point that's at the origin stays there, because 0 times anything is 0. But the rest of the points expand out away from the origin as you increase that. And negatives would reflect it through the origin, because negative r's come out the other side. So you could even have a negative out front. And the same thing would happen with cosine. Now, what's a lot more interesting is playing around with the wavelength of this sine. By messing with A, we can either compress or stretch sine, but that's going to increase or decrease the amount of times it enters or leaves the origin. Let's slow this down, and we can get some pretty crazy spirograph looking graphs out of this thing. Now we're going to keep it simple. These are quite complicated because the curves overlap each other. All kinds of interesting things happen, but for our purposes, for doing some calculus, we're going to look at when these are just nice integers. So let's go say in step by 1. And now look at what happens. So when a is 1, you get 1 loop. And then as it moves forward to 2, you get 4 loops. So you get twice that. And then when you move to 3, you get 3. And the pattern is, if that factor is odd, you get that many leaves, as the book refers to them. If it's even, you get double the amount of leaves. So since we're at 4 right now, we have 8 leaves. 3, we only had 3. So as we move to 5, we go back to just 5. 6 will give us 12, and so on. And really what's happening is they're all giving us double. It's just that when it's odd, the second time around, they draw on top of each other. So that's 12 unique ones. But this 7 is really 14 leaves. As it goes around, it draws all 7, and then it draws all 7 again because they're perfectly in phase with each other. Whereas on the evens, they're just perfectly out of phase so that you double them up. And of course, the same thing would happen with cosine as well. Again, just rotated about the origin. So that's what cosine looks like at various a values in blue and sine. But always with that same shape, but rotated.